Okay, welcome to the lecture on Chapter 13, and this is part 4. Oh no, my data is not linear. Here's the example. The moisture content of marine muds that accumulate in small inlets on the Gulf Coast is of interest to geologists in eastern Louisiana. The following measurements of the moisture contents of core samples were obtained by comparing the weight of a sample immediately after its removal from the core barrel with its weight after forced drying. The moisture content is expressed as grams of water per 100 grams of dried sediment. We wish to relate the moisture content to the depth in meters of the core sample. Okay, so we're going to do a linear regression analysis on this data. And first thing we need to do is enter the data into our calculators. So I will bring up my TI-84, and let's see, I need to do that. Okay. And I'm going to I'm going to press Stat, select Edit to go to the editor, and I actually already have these lists in my calculator. But let me review how you would enter these named lists. So I'll just delete those out of my editor and pretend like those weren't there. And it doesn't really matter what your editor looks like or whether or not you have the same lists that I have, L1, L2, and L3. But what you need to do is move your cursor all the way to the very top. Notice here I have L1 highlighted as far up as I can go. And I'm going to press second delete. What this does is inserts a new list. It's waiting for a name. So I'm going to name this list depth. Okay, and then I press enter. Now, when my list comes up, it has numbers in it and actually has the data in it already. So what I've actually done here is I've opened up a space in the editor, and what I've really done is pasted the list into the editor that I have already entered at an earlier time. And I'm not going to go through re-entering this data because I think that we've done this enough times now that you're probably becoming comfortable doing that. So as a matter of fact, if I keep rambling on here, you'll probably have the data in this list before I finish talking. If not, just press pause and enter the data. Okay, now I'm going to put the moisture list in my calculator, and I'm going to go through the same process. Second, delete, inserts a blank list. Now, when you're trying to insert these lists, if you ever get an error message, it's most likely because you didn't have your cursor all the way up to the top. So you were trying, or what can also happen too is if you have your cursor down in the body of a list and you do second delete, you'll insert a space in that list. So if you want to insert a blank list, you need to have that cursor all the way up to the top. Okay, so I'll name this list moist. Press enter. And again, I've already entered this data into my calculator. So, and I'm not going to go through that. I won't go through that process again. And if you need a minute or two to enter the data, just go ahead and hit pause. But I'm going to move on. And let's see, didn't mean to press that button. All right, so I'll move on and start into the analysis. So the first thing I want to do here is draw a scatter plot. 3 steps for drawing a stat plot. Enter the data. I've done that step. Step 2, configure the stat plot window. That's second y equals. I'm going to use plot 1, so I'll select it. I need it turned on. The type is a scatter plot. X list is depth. Y list is moist. And again, if you need time to set up your calculator, just hit pause. Make your screen look like mine. Okay, so, and the third thing I need to do to draw a stat plot is configure the window. In other words, scale the axis under window. Scatter plots work really well with another feature though, zoom 9 for zoom stat. And whoops, oh my goodness, the cat's out of the bag. I Forgot to turn these or to eliminate those equations. I worked through this whole problem ahead of time. Any case, all right. So this is what the scatter plot should look like. And if you get like a graph or a line going through your graph like I just did, it means you had something in y equals, okay, on, or an equation in there, and you just need to go in and clear that out like I did. All right, so this is the scatter plot we should be looking at. So when I look at this scatter plot and I start to think about what would the theory be here, and notice I did look at the scatter plot this time before I started talking about setting up a hypothesis and thinking about what the theory would be. But let's talk about the theory here for a second. So we have two variables. We've got the depth, and then we have the moisture content. And I'm going, and the idea here, or the question is, or the theory would be, that either the depth is linearly related to the moisture, or the moisture is linearly related to the depth, and one is going to depend on the other. And I think it makes sense to think about the moisture content being related to the depth. And what I want to think about in the, and of course we're going to start out with a linear model, but the moisture, the theory here I think that makes sense is that the moisture content decreases linearly, okay, because we're going to always start with a simple model, linear. So our theory here should be that the moisture content, what am I spelling? I knew something looked wrong there. That the moisture content decreases linearly as the depth increases. All right. And as we think about this, we want to also think about our variables. So I'm going to make moisture content my y variable because I'm assuming that the moisture content depends on the depth. So I'm going to make that depth my x variable. And then decreases. And then this is going to be part of the theory that affects beta. Okay. Now, one thing I want to point out, I'm going to go back to the calculator for a second. I want to point out that, whoops, I thought I was. Let me try that again. All right. Now, the trend in the scatter plot is also a downward trend. So notice I graphed depth versus moisture. Okay, that's how I set up my plot. I didn't talk about the x and y variable as independent and dependent when I drew this. I just did it. But as we're thinking through the theory now, I want to look at the scatter plot and see that this pattern is consistent with the theory that I'm bringing forth about the relationship of the variables. That's a mouthful. But the idea here is that it kind of makes sense that the deeper you go, the further away from where the water would have been you get, right, as you go down. So the content, the moisture in that soil as you go down should go down. So that's like thinking about that, what is actually happening in the system that we're modeling. And then the data, the scatter plot, which is the data, is consistent with that. So that's a good thing. So our theory, okay, which I just lost, I'll write it one more time. The theory is that moisture content decreases linearly as depth increases. And moisture content, this is our y variable, depth is going to be our x variable. And so the model that we're talking about for the population, so this is the population model, always we're modeling the population, is going to be y equal alpha plus beta x. And beta is the slope that we're interested in. So as I begin to construct my hypothesis, my statistical hypothesis, which is always in two parts, a null H0 and an alternate H1, the theory is going to go into the null. I'm sorry, I said that wrong. I was pointing at the alternate. The theory is going to go into the alternate. Okay, so the theory is going to go here. And the theory is that the moisture content decreases as depth increases. So that means the slope is less than 0. If the theory is true, the slope of the line should be less than 0. Now the null theory, okay, the null theory, which is our nothing theory, is that there's no relationship between the variables. And that's always the null theory for a linear regression analysis. Okay, so now we're ready to do our lin reg t-test and see what the particular values are. Specifically, since I now have a hypothesis to test, I want to know what is the p-value, okay? The other thing I'm going to be looking for are A and B, because that's what's going to tell me what the best fit line is for the data. And remember, we always have two versions of this equation. We have the population version up here. Okay, this is the population version. And then we have the version that estimates that model that comes from the data. Okay, and that's why we have different symbols, A and B for the data, alpha and beta for the population. The null is about the population, so that's why I have betas in there. And that's a common mistake I see students make, is putting B's instead of betas in here. And I don't know why, but I mean, I guess I assume it's because the confusion is that about what we're modeling. Are we modeling the data, or are we modeling the population? The hypothesis is always about the population. Therefore, the statistical hypothesis will always be written in terms of parameters and not statistics. Okay, let's just review that. I just want to make sure everybody's understanding this. Alpha and beta are values, they're hypothetical values, they're from the population, they're parameters. If we could sample that whole population, right? Imagine that. We got a bay and we're sampling mud from a bay. Well, how many samples are possible? I mean, alpha and beta, we got to believe they exist, but we have no way of measuring alpha and beta. But instead, what we're going to do is we're going to collect a data set and we're going to find A and B. And alpha is approximately A is approximating alpha and B is approximating beta. And these are what we call statistics. The rare event principle, okay, means that is B, the question here that we're asking with our p-value is B, or let me say it this way, how rare and unusual is B from the data given our assumption that beta is equal to 0. So if you look at the null, now when we do a hypothesis test, we're assuming the null is true. The slope of the true line is 0. We should get a b value close to 0. If we get a b value that's smaller than 0 by a long shot, that means that b value is rare and unusual, and we should reject the null. That's what the p-value is going to tell me. And then the other one of the other key statistics I'm going to be looking for is R squared. And R squared is the proportion of variation in moisture content explained by depth, the depth variable, using a linear model. So in other words, when we look at the original data, all of the moisture contents were different, and so they're varying from each other, and there would be an average moisture content for all of our samples. And what R squared is going to tell me is what of that initial variability, how much is being explained by using the depth the sample was taken. Okay, so let's switch over to the calculator for a minute, and we'll actually go through the linear regression t-test process. So I'm going to go out, I'm going to press second mode, which will take me back to the home screen. I didn't actually need to do that. I don't know. I just have a habit of doing that. I could have went straight to stat and tests. And then I'm going to find linear regression, linreg t-test, select it. And what I want here is X list is depth, and I want the Y list to be moisture, for moisture content. So I'm going to go, let's see, I need to go second stat, and I'm going to find moisture, or moist, I guess I named it. Whoops, oh, holy moly, what happened there? Let me try that again. Oh wait, you know what? The smart thing to do here is to go alpha M, which takes me right to moist. Okay, that's a shortcut. All right, and frequency, we'll always leave that 1. The alternate, now the null is always the same, so there's no place to put any information about the null in this window, because it's always beta equals 0. But our alternate assumption, if you remember, is that beta is less than 0. So I'm going to pick the less than 0 choice. Regression is y2, the regression equation. I'm now telling the calculator at the moment to store it in y2. I want to change this. I'm going to store this as y1. So I just press vars. I'm going to yvars, function, y1. Okay. And what the calculator will do is automatically paste the equation of the best fit line into y1. Now we'll press calculate. And p-value is fairly small. It's about, oh gosh, you know, that's about 1 in 1,000. We'd see this data about 1 time in 1,000 if the null were true. That's pretty strong evidence against the null. There's A and B, and R squared. About 79% of the variation in moisture can be attributed to the depth the sample was taken. That's pretty big. And of course, there's R telling me that I had a negative correlation, and that the magnitude is about 0.89, which is a pretty strong linear relationship. And let's see, as long as I'm looking at the calculator, the next thing I can do is look at a graph. Now, since I had the calculator automatically store the regression equation in y1, when I press graph, I see both the scatter plot and the line together. And the line looks like a pretty good fit. So let's take a look at what all of these things mean, okay? So to recap, the null hypothesis is no linear relationship, beta equals 0. Alternate is negative linear, that's a less than 0. The p-value here is approximately 0.0015. This p-value tells me that it's very unlikely that we would sample this data if there were no linear relationship between moisture content and depth. Therefore, we should reject the null hypothesis and accept the alternate. The data provides statistically significant evidence that moisture content and depth are negatively correlated. Okay, so now there was more than one way to say this, all right? But one of the things I'd like you to really start working on is trying to write a few sentences explaining what these numbers mean, because that is so important in statistics to be able to it's vastly more important and useful to be able to explain what these values mean instead of simply being able to find them. And like I tell my classes often, um, you're going to have a relatively easy time finding people to help you figure out what the right p-value is for your data, but you're going to be having more difficulty finding, especially faculty, I think, that'll help you explain what it means, because that is really the critical thinking part of the whole process. But in any case, like I said, many of you are doing a really great job explaining what these things mean, and I'm really happy about that. So keep up the good work, but try to really, and again, I'll mention I have a tendency to really be forgiving when I grade students. I want you to not be afraid to say what you think, because you're going to lose points. So I really try to be very forgiving and generous when students are really making a hard effort or an effort to explain what it means. Um, and again, playing it safe, I think, is to write a few brief things that, that like you think will capture the most points or whatever, but really try to be, don't worry. What I'm trying to say here is that I reward students for the effort of trying to explain these things as much as being correct. I think that's what I'm really trying to say. And I understand the anxiety about not wanting to write something and because you think it's wrong. In any case, I just wanted to say that. So let's go on through these values and look at some of the other how we can interpret and what some of the other numbers mean. So that's the hypothesis test and the conclusion. Now, the other part of the story here is the actual equation that we would use to make predictions. Okay, so linear regression analysis is really a fascinating area. because there's many uses. Like one use is to say, is there a significant relationship? And I'm going to do another video real soon, the last one for chapter 13, where that's the whole focus of the analysis. Is there a linear relationship? But there's also sometimes an interest in actually making predictions. And so the idea is that if I need to predict what the moisture content is going to be at a particular depth in this bay, and engineers, I can easily understand how an engineer would be interested in this, perhaps. So the idea here is, the way to think about this is, do I use the average moisture content as my estimate, or do I bring in this depth variable and try to establish a linear relationship between the variables? In this case, that's exactly what we're doing. We're doing the latter, and since we have a small p-value, we can do that and say that that's a statistically significant thing to do. The actual equation that we're going to use is has the form y equal a plus bx, all right? The hat means y is a estimate, okay? It's not the actual population value. The hat, just like x bar, when we used x bar, we have to signify to the reader of our analysis that this is not the true y, this is the predicted y that comes from data. In any case, that's why we have to have that circumflex or that hat on the y. Now, the calculator gave us estimates for a and b. So the way I'll write the equation is I'm just going to replace a with an estimate. Now, I'm not going to get too crazy here. I'll round a to the nearest hundredth. And let's see, b is negative, and that's good. We expected b to be negative because the relationship we thought was a negative linear relationship. And then there's my x. So this this equation is the actual equation we would use to make predictions. So for example, if I needed to make a prediction of what the moisture content would be at, say, I don't remember the units on this now. I'm just going to not worry about units for a minute here and just say at x equal, I think this was feet, say 18 feet. Then my prediction would be y hat equals 94.67 minus 2.68 times 18. So I just plug the 18 into my equation and figure out what that's equal to. So let me get my calculator. Oh, of course, well, let's see. Second quit. I'll just do this on the home screen. So 94.67 minus 2.68 times 18 is about 46. Grams. I had to go back to the original problem. So the units are grams, and what is the unit in depth? I'm just curious. I think it was feet. Oh, meters. Rats. I was wrong. All right, meters and grams. That would make sense. Duh. All right. So now let's go back. Wait a minute. And let me just make a note of that. So the depth would be, so that at a depth of 18 meters, the moisture content would be 46.43 grams. Okay. Now there's one other statistic here I want to point to, which is our R-squared value. So R-squared is called the coefficient of determination. And what R-squared measures or tells us, R-squared is the proportion of variation in y explained by using x in a linear regression analysis. So notice I try to write these things using different sentences for a couple of reasons. One is because I think it helps people remember to hear this in different ways. And the other is because I think students too often, I fell into this trap when I was a student myself, tend to memorize definitions without really understanding what they mean. And in statistics, memorizing a definition without really understanding what it means is just really a waste of time. So, and again, I've noticed already, many of you explain things very well in your own words. So I encourage you to explain these things in your own words. And again, the idea here is that R squared, it's a proportion. What is it a proportion of? It's a proportion of the total variation that was in the Y data originally that's being explained when we use the depth the sample was taken at in a linear model. In this example, R squared is about 79%. So I've converted the decimal to a percentage. So 0.79 equals 79%. Okay, so the way I would write this up, or my interpretation up, is I'd say approximately 79% of the, I'm going to say it this way this time, original variation in moisture content can be attributed to the depth the sample was taken using a linear model. So what's important? 79%. Percent's important, okay? It's a proportion. What else is important in the explanation? We're talking about variation, percent of variation. However you word this, that's the idea. R squared's quantifying percent of variation attributed, explained by X, the depth. So as you begin to construct these things in your own words, look at that framework. It's a proportion, percent of what? Percent of variation. There's a total variation, some's explained, some's not explained. Another piece of this puzzle is that the fact that 79% is explained means 21% is not explained. Is the only factor that affects moisture content in these muds the depth the sample was taken? No, probably not. As you go down deeper, the type of soil probably changes. That's another variable. Now, of course, most of the time, this is an important thing about regression analysis. When we're making predictions, we're actually looking for variables, independent variables that are confounded with a bunch of other variables. So interestingly, when we're talking about regression analysis, X being confounded with a bunch of other variables is a good thing. And that's because our goal here is to make a prediction. So what we're looking for, ideally, is the most important variable. we know there are other variables as well. Now, let's think about that for a second. The type of soil is another variable, but is the type of soil related to depth? I would argue it is, because most likely, I'm going to draw a little mini picture here, right? You've got, if you think about it, you've got the bay water above. Now, of course, the tide's probably out when the sample's collected, but a lot of the time there's water above. And so how do these bay muds accumulate? Well, they're stratified. So certainly the type of soil, or the type of soil as we go down, is going to make a difference, right, in terms of the moisture content. But when we drill down into this, right, since most likely this soil is in different stratifications, that depth is going to account for that variable, right? Now, also, the water is being probably pushed down from the top into these muds, right? So the deeper you go down, the less moisture you would expect to find probably in the moisture content. So all of these things are confounded into this variable that we're talking about, depth. And that's why 79% is being explained. Now, certainly there can be variation, right? Because like here in Humboldt County, well, I'll just play around here. I'm not a geologist. I know a little bit about geology. You know, in Humboldt County, we get these natural gas bubbles that form, and they can morph, right? This instead of being that linear looking stratification, maybe geologically these have morphed. And so all of a sudden now our different core samples are introducing variability. Well, that variability can't be explained as well by depth, if that's actually what is happening. Now, I don't know if that's what's happening or not, but that's why instead of having 100% of the variation explained, I'm not surprised to see that we have 79% explained. Okay, so a lot to know in linear regression analysis. It's a very rich field, many different pieces. And again, like I've said before, I really think of regression analysis as putting pieces of the puzzle together. So far, the pieces fit. Now, there's another type of analysis that we need to do, which is a residual analysis. So let me go to the calculator again and show you how to do the scatter plot for the residuals. So what I'm going to do is, all right, scatter plot is a stat plot, 3 steps. First step is to enter the data. Now, what we need is the residuals, okay? Let me go back to PowerPoint for a second and remind you what a residual is. The residual is the observed y value, say for 0.1, observation 1, minus its predicted value, and oops, and that's not an I, it's a 1, and that's going to be the first residual. And so each one of the observations has a corresponding prediction and has a corresponding residual. So what we need is we need our residuals into a list, okay, on the calculator. Now, it turns out that the calculator, that residual analysis is a fundamental part of a linear regression analysis, and so the calculator already stores those residuals automatically. So just by doing a linear regression t-test, the residual list is created and the residuals are pasted into that list by linreg t-test. Okay, so the data's already in the calculator. Second step would be to configure stat plots. So I'm going to go second y equals to the stat plot menu. And, oh, I'll just use plot 1 here. That's fine. I'm going to change, and this is what I normally do. So it needs to be on, and it is. It's a scatter plot, so choose the first icon. Now, residual plots, we always leave the x-list the same, and we compare the x's to the residual. So I'm going to get rid of moist. I'm going to go second, stat, and I'm going to look for the residual list. There it is. So I'll select resid. That gets pasted in as y, and now I need to scale the axis. So I'm going to go, that's the third step. So I'm going to go zoom 9. And this is what the residual plot looks like in there. Lo and behold, I left the y on inevitably. So let me show you how to deal with that. Now, press y equals. Now, we could clear it out, but I actually want to save this equation. So I'm going to move my cursor over the equal sign and press enter. And notice how equal sign's no longer highlighted, that means I just turn that equation off and the calculator won't graph it now. Okay, I've reproduced this scatter plot in PowerPoint. Now, I hope you recognize this pattern, okay? This is what we call a curvilinear pattern. And what it implies is that a nonlinear model may be more appropriate. All right, now the residual plot magnifies any kind of systematic varying of the data, of the observed values with respect to the line. So when I go back and I look at the original scatter plot, okay, and remember we put a line through that scatter plot, and so I see that the first residual is positive, which means this point was above that line, and then these other ones are below, which means they were below, and then these are above. But the main thing I want to point out here is that if you look really carefully at this scatter plot, it almost looks like instead of linear, there's a curve happening here, okay? And some of you may recognize this as the decaying exponential. So the model, so what I'm doing here, or what's happening here, is that the residual analysis is taking me back to my original assumptions. And my original assumption was that the model was linear, but now I'm questioning that. Now I'm thinking, wow, maybe instead of linear, this is a nonlinear model, like an exponential model. And so what is the classic exponential model? This is a Math 120, or this is an intermediate algebra idea. P naught for the initial population size, and again, some books use, I'm a population modeler, so I just always put P naught. But there are, let me just write down, and then E to the RT, where rate is the rate of growth or decay, and T is the time. So this is kind of the classic model. This works, I mean, P naught works if you're modeling populations, modeling money. This could be the initial principle for continuous compounding. But some books and some people look at this model also with a capital A, E to the RT, and there are actually more than one way to write the model. Okay, now what I want to do though is I want to be consistent with our book's notation for these constants, and so I'm going to actually use lowercase a and b in place of r and x in place of t, okay? So this is the same exact model. It just has different letters for constants and a different letter for the independent variable. Now, generally, t is time in the exponential model, but it doesn't have to be that way. In this case, I'm saying x is depth, and y, the moisture content, is related to depth in an exponential fashion. And that's nothing wrong with that. Now, the way I'm going to do the analysis is via a transformation. And the transformation I'm going to call a linearization. So, you know, is statistics confusing? It most certainly is. I mean, we've had the concept of standardization transformation, which is something we call a linear transformation. And that's not actually what I'm talking about here. I'm talking about taking my nonlinear data, transforming it into linear data, and then proceeding with a linear regression analysis. And if you're out there going, what did he just say? Let me explain it in a different way. Lin-reg t-test is designed for models y hat equal a plus bx. We're saying that the model we want to use is nonlinear, okay? Can I transform this equation to a linear equation, okay? Or another way to think about it is, can I take my data and transform it into more linear looking data? Well, the answer is yes, because if I take this equation that I'm going to use in the model here and take the natural log of both sides, do some algebra, what we see is, now technically this is not a linear equation, okay, because the natural log of y is not going to end up being all I've done is really taken the inverse here, but nonetheless, let's just continue to play around a little bit and see what happens. Now, this I'm going to notate with a hat over it, because now I'm going to model this whole thing like ln of y as a variable, okay? This ln y hat is going to be like y hat over here, but it looks different, okay? Because I'm going to do I'm going to do a linear transformation, then redo the analysis, okay? So next thing I want to do is show you how to modify the data on the calculator using this transformation. So the algebra here is really meant to tell me what to do. This tells me what to do with the original y data this tells me what to do with the original y data. Okay, and what do you do? Let me do it this way. Question this: what do we do with the original y data? The answer is, all right, drum roll. Take the natural log of, I'm going to be specific, list y, which in this case is list moist. Okay, so let me show you how to do this on the calculator. All right, so this is going to be a list operation. So I'm going to go to stat, edit, takes me to the list editor, and I'm going to insert a new list here, okay? So I move my cursor all the way top on L1, second delete, and I'm going to call this new list ln MST, ln moist, boom. All right, there's already stuff in mind because like I said, I worked this out ahead of time. I'm going to clear this out though. So I want to show you how to actually do this transformation. Now I want to point something else out too. Right now my cursor is in the wrong place, okay? If I try to do the natural log of all the moistures and leave my cursor where it's at now, I'm going to get an error. And the reason is because when I take the natural log of all the moisture data, I get another list or another set, and the calculator is expecting a single number here. If I try to put a set in there, it's going to give me an error. So what I have to do is move my cursor all the way to the top. Now I have the entire list, ln MST, selected. So now the calculator expects me to put another list in there, or a set in here, okay? What we need to do is take the natural log. So I'm going to press ln. And I want to take the natural log of all the moisture data. So I'm going to go second, stat, and choose moist. That's the list I want to take the natural log of. close the parenthesis, press enter. Now what's in list moist is, or natural log moist, ln moist, this is the natural logs of all of the moisture data, okay? What we're going to do next is look at a scatter plot. Basically, what we're going to do now is redo all of the linear regression analysis that we did before using the transformed y data. So I want to look at a scatter plot. So I'm going to go back to plot 1. I'm going to switch the y list from residual to second stat. I want ln moist. Now I'm going to go second L, and that'll take me right to the right list. Yeah, and then enter. Rescale the axis with the zoom 9. And visually, the data here looks more linear. Okay, and that's good. That's a good sign. We're going to redo the linear regression analysis. So I'm going to go stat, test. I'm going to do the linreg t-test again. But this time, instead of doing the linreg t-test on depth and moisture, I'm going to switch moisture out for the natural log of moisture. So the idea here is that the transformation is going to linearize the data. And I'm not doing, let's see, alpha L is the shortcut here. There we go. And let's see. All right. Now, same theory. As depth increases, natural log of moisture would also decrease. So I'm going to leave everything pretty much the same. Now, I want to clear this out because I do not want, I'm saving the linear equation for comparisons at the very end of the example. So I don't want to have, if I left y1 there, when I redid this analysis, it would actually have replaced the linear equation with this modified linear equation, which I don't want to do. So I'm going to leave that blank and then go to calculate. Wow, already I'm seeing the smaller p-value. A and B we'll talk about in a minute. R-squared went up to about 94%. So this is an overall improvement in the model, okay? So what's important to see here as we do the analysis is that we've actually improved the model, okay? Now, both of the p-values are significant, so that isn't really the main thing, okay? It's certainly, you know, for the linear model, okay, the p-value was, it was about, well, I think it was about 0.0015. And now for the nonlinear model, okay, or the exponential model that we're looking at, the p-value is about, let's see, 0.00004, okay? So yeah, it's a smaller p-value, it's more significant, and that's good. That means the model's improved. But the thing I really want to focus here is on R-squared, okay? Because R-squared for the linear model was well, I'll write it as a percent, was 79, let me write that better, 79%. That was the linear model. And the nonlinear model, okay, or the exponential model, we're now up to about 94%. And that's huge, okay, because what that tells me actually when and again, pieces of the puzzle, okay, part of why I was not explaining as much variation here is that there was a better model. The exponential model was better. All right. So we can have so yeah, and so that was one of the key things. Now only 6% is left unexplained, okay? That's remarkable. This is telling me that the depth the sample was taken is by far the most important variable here and the best predictor of moisture content. It's just that I should be using the exponential model and not the linear model. Okay, so let's go back to the A and B part of this, okay? So what we're modeling here, okay, with linreg t-test is ln of y hat, that whole thing, equals a plus bx. So ln of y hat is equal to about 4.59, that was a, minus 0.05x, and negative 0.05, and these are approximations, that's about b. Now, certainly I could take an x value. So again, if I were interested in estimating the moisture content for a sample of mud taken at x equal 18 meters, then I could certainly model it using this form of the equation. In other words, I'd have the ln of y equals 4.58 or 4.59 minus 0.05 times 18. I could get an approximation here. I'm pressing buttons on my other handheld TI right now because I don't want to lose what I'm writing. If I went to the virtual one online or on my computer, I would lose this. So let me just, so this is about 3.69. Now, I'm not going to put units of grams here because this would be wrong, because the problem is, this is really the natural log of y that's equal to that. And so the actual estimate is going to be, I'm going to reverse the transformation, okay, by raising both sides to the e power. And that's going to equal e to the 3.69, okay? So e and ln are inverse functions, so y hat, so they, in the composition, they undo each other, so we end up with y hat, and y hat is equal to e 0.369. And again, I should be using approximates, but I'm pretty lax with that in stats because we're into ideas here. So this is modifying the estimate to 40.04 grams approximately, okay? So I have to undo the transformation to get back to the correct units of the original data. Now, it's probably better to actually write this whole equation transformed back to the original units that we were working with, because when I do the transformation, I mess up all the units, right? Because I'm taking the natural log of all those y data points. Now, I'm ripping through this algebra, and the main reason here is because your ability to do the algebra is not something I'm going to test. I think nonlinear modeling is starting to stretch the concept of this being of this being an elementary stats class. So my actual model here would be e to the 4.59 and then e to the negative 0.05. Now, normally we would write this also. I can modify this by actually calculating e to the 4.59, and that's this is actually going to be approximately. Actually, let me write it like this. E to the 4.59 is approximately equal to 98.49. And so the model, I would probably, I would simplify to so now, if we go back and look at the original scatter plot, okay, I'm going to go back and let's see, what do I want to, I'm going to set up, I'm going to go second y equals, okay, I'm going to go back to the original data, because remember, the transformation is an intermediate step. And really what we're interested in is modeling the original data. So I'm going to go back to the original data set. I'm going to go into my Y menu. Now remember, I had in Y1 I have the best fit line for the data, and now I'm going to put in the best fit exponential function for the data, okay, which is going to be 98.49 times E to the, I'm going to put parentheses here, negative 0.05 times X. Close those parentheses. And now I need to do a zoom 9 as well because I need to rescale my axis. Now there is the line, and what I hope you're noticing is that what we've done basically is we've modified the line into a curve. Or I don't think that's what we did, but but we have two different models here. We have a linear model, we have a curving model, or an exponential model, and it looks like visually the curved model is fitting the data much better. So now if I do a trace on these, I want to go back and talk about that estimate we did at 18. So if I go to 18 on the line, that was about 46.4. It was an overestimate. If I hop down, I get the other estimate of 40.15. And you can see that it makes sense that that moisture content should be a little bit less because the data is showing this curvature. So what does this all mean? Well, okay, let me summarize. So here's what we do. We do the linear model first because it's the simpler model. Okay, so I can't spell today. It's the simplest. Okay. KISS. This is one of the things that my professor would always tell me. And KISS stands for keep it simple. He said stupid. I'm going to say student. All right, in any case, keep it simple. We start with the simplest model. Y hat equal A plus BX is the simple model, okay? And what we ended up with is a p-value that's significant. We end up with an R-squared value that's pretty good size and explaining a lot of the variability. Residual plot, everything looked good until we got to the residual plot. It told us a nonlinear model might be better. So we started with linear, looked good except for the residual plot. That's the piece of the puzzle for linear that didn't fit. Then we went to the second nonlinear model. Hoping to improve the fit. So we did a ln transformation to the original Y data because the pattern in the scatter plot, and this is the original scatter plot, looked exponential. And you might be thinking, natural log transformation for an exponential pattern? It's because natural log is the inverse of base E exponential. This is a little bit paraphrased, but that's the idea. So we use the inverse of the relationship we think we're seeing because the natural log undoes the exponential. So if I have exponentially decaying data, if I natural log the y, I should see more linear data. And then we redo the, then once we do the transformation, we redo lin-reg t-test using transform data. The actual model was y hat equal a e to the bx. We found p-value to be smaller, and we found r squared to be quite a bit bigger. And so this is telling us we've improved the model and that we should we'll abandon the linear model and we'll use the improved model for our predictions. There's one last thing I want to show you on the calculator. So let me go back to the calculator here for a minute. Now, some of you may, sometimes you get into this regression idea in algebra, in intermediate algebra, and it isn't always, well, I don't know. I don't know. Usually in intermediate algebra, I don't think you end up with nonlinear modeling, but certainly you do, I think, sometimes linear regression modeling. So I'm going to the calculate. I just pressed stat and I went to calculate. Notice this is the lin-reg option here. But I know that if some of you have been searching around here, which happens pretty much every semester, you might have ran across in this list of all these different regression options, exp-reg. And you might be saying, well, why not use exp-reg? All right, well, let's talk about that for a second. So I just selected it, came to the home screen. I'm going to do an exponential regression on the same set of data. And I'm going to go to, and the way we do it is I went to stat, calculate exponential regression. I've got to list the two variables now. So the variables are depth and moisture. Depth, and then the syntax is depth, comma, moisture. Okay, and if I press enter, I get the A and the B printed out here. And notice there's nothing else printed out, okay? And that's because the diagnostics aren't turned on. If I had diagnostics turned on, it would print out R and R squared, but I'm not going to bother with showing you how to do that because we're not using that feature. But what I do want to point out, in case you've been playing around with this, you'll notice that A is the same, okay, because it's the constant coefficient out in front here, but the B is different, and what you have to be very clear about is the form of the equation the calculator is using is different than the form of the equation I was using. And let me show you the difference. Now see, it says A times B to the x. Okay, so let me go back to PowerPoint here and try to explain this. So the model well, it's the same model, okay? It's just a different form. So I was using this y hat equal a e to the bx, okay? And the reason is because when I did the transformation, naturally this is going to look like the same form that we model with the linear model. But this equation is also equivalent to y hat equal a times b to the x. Okay, and again, we have to do a little bit of algebra to see that. Clearly, the a's here are the same, and the values we got both ways were the same for a. So in both cases, both forms, a was approximately equal to 98.49. But what's really happening here is when I did the model, okay, let me write down the two versions of the model. So the one I had was y hat is equal to 98.49 e to the negative 0.05x, okay? And the book, or I'm sorry, the calculator has y hat equal 98.49 times their b value, which is 0.95123 approximately, I think. And that's raised to the x power this way. And that's because the b here is being exponentiated. Now, that means if both of these equations are equivalent, then it's got to be true that e to the negative 0.5x is equal to 0.95123 to the x. That's not squared, to the x, okay? So on this side, doing a little algebra, I've got I have a product in the exponent. That means I can rewrite it as an exponential, e to the negative 0.05, and then that whole thing raised to the x. And so now what I hope everybody's seeing is that the actual bases we're talking about that are comparable, okay, is the e to the negative 0.05. So if so what we're saying here, or what I'm trying to say, is that this implies that e to the negative 0.05 is approximately equal to 0.95123. And if I go back to the calculator and just do that, just to verify that the algebra all works out here. Whoops. Let's pick calculator. Okay. Let's see. So what is e? Shoot. Second ln. What is e to the negative 0.05? It's about 0.95123. So yes, that's what's going on. But in any case, the reason that I don't use any of the regression methods under calc, and I use Linrake t-test, is because we're doing hypothesis tests. So we wouldn't get a p-value with those other tests, and that's one of the reasons I use the linear transformation idea. Anyway, I'm going to stop talking now, and I'm just going to say the end to this presentation. It's been a pleasure. I'll see you don't miss part 5. In part 5, we're going to investigate whether or not Elvis knows calculus. Have a great day.